Good morning, and thank you for joining us here on the Morrison Planetarium Facebook page. My name is Ryan White. I'm Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and it's a great pleasure to be joined today by Amy Mainzer, who is at the Lunar Planetary Lab at the University of Arizona.
Hey, Ryan. Thanks so much for having me on.
Absolutely. Thank you for joining us, and with fortuitous timing, with the recent news about OSIRISRex and Bennu, this is a perfect time to be talking about asteroids, and I can't imagine someone better to talk to asteroids about than you, Amy. So thank you for taking some time to talk to us today.
No problem. Well, this is a really exciting year for asteroid science. We've got all kinds of stuff going on. And, just to remind people of why scientists are interested in asteroids, it's for a variety of different reasons. Of course, we love them because they're scientifically really interesting. They are very, very old in a lot of cases. So you can kind of think of them as time capsules, if you will, from very early on in the solar system's formation. But we also care about them because sometimes they impact the Earth and they can have effects on the Earth's biosphere. So lots of reasons why we pay attention to these objects, and you can imagine that everybody who looks at them from the science perspective, sees something different and interesting that they care about.
Very, very complementary reasons too. Both the sort of cerebral appeal of the scientific interest and the very practical reason, like we don't really want to get hit by these things, so it's good to know where they are.
Exactly. So the OSIRISRex mission joins Hayabusa 2 and the previous Hayabusa mission. So there's actually 3 asteroid sample return missions now. One of them was completed a few years ago by Japan Space Agency, JAXA, and it brought back some very precious grains of an asteroid called Itakawa. So that actually has been analyzed in the lab, and people have used those results to help set benchmarks on the timing of when events happen in the solar system's formation. Now we're looking forward to the return of not 1 but 2 more large samples, and in this case, we're hoping that we don't just get grains, but we get bigger chunks of material. So the Hayabusa 2 mission is actually about to return its samples in, I think about a month. They're going to be returning their sample capsule. So we're really looking forward to that. Talk about an unboxing video. That's going to be really, really exciting to see what comes out of that mission. And then also OSIRISRex just collected its sample.
Right.
That's going to take a little while to come back to Earth, but it's looking really good. So that's great news.
That's great. So I think we're going to start our story here on Earth and then make our way out into our virtual universe and explore some of these locations. Maybe starting out with a kind of scary event that happened about 7 years ago now.
Yeah, time flies. But this was quite a record day in the asteroid world, so to speak, because actually, coincidentally, we knew that there was supposed to be a close approach of an asteroid, but it was also well known that it was not going to impact the Earth. So when this occurred, this was a real surprise. But it turns out this was a completely different asteroid. We know this because it came from a completely different trajectory on the sky. So this object impacted over Russia, the city of Chelyabinsk, and it basically created a large fireball explosion many kilometers up in the air. It was an airburst. So Earth's atmosphere acts as a very powerful shield that protects us from a lot of smaller impactors. And in this case, the atmosphere mostly shredded this object into tiny pieces, some of which we have on the ground now. But what happened is the shock wave from this explosion high up in the atmosphere was enough to shatter windows all around, and it injured in total about 1,600 people. Largely because what happened is people saw the flash in the sky, but because it was so high altitude, it took time for the shock wave to propagate down to the surface of the Earth. So people saw it and they ran to the windows to look at what was going on, and then the shockwave hit and broke a lot of windows. Yeah. So it's very scary for people. But basically, the reason that impact is important to us scientifically is because it's one of the very best measured events. Nowadays, we have cell phone cameras and dash cams and security cameras, and so there's a lot of great footage from that event, in addition to all the little pieces that were picked up on the ground that allow us to say something about exactly how the object broke up in atmosphere, where it came from, and all of that. That said,
there were so many cameras that were actually able to reconstruct the trajectory in 3 dimensions, right?
Yeah. And of course, it brings up the question, well, okay, if we know so much about its trajectory, why didn't we predict it? And the answer is there's a couple of reasons. One, this object is was relatively small. It was about maybe 17 or 20 meters across. And I think you've got a great animation.
Yeah, we can show you relative to, we're actually hovering here over the music concourse in a virtual space. And here's an artist rendition of what the Chelyabinsk meteor might have looked like. It's about the same size as Morrison Planetarium, we're fond of pointing out. So if you've ever been inside the Morrison Planetarium, imagining a rock that big is a little terrifying.
Yeah, and so, I mean, you might ask, well, okay, if a planetarium-sized rock hurls at the Earth, what happens? Well, in this case, this is a planetarium-sized rock that's moving at something like tens of thousands of miles per hour, or maybe somewhere between 10 and 20 kilometers per second for this particular object. So that's really fast. It's just incredibly mind-bogglingly fast. And even something that's just the size of a building is capable of causing a lot of damage simply because it just has so much kinetic energy, the energy of motion. And that depends on the speed squared. So it's not just a speed, but actually speed squared. So in this case,
we were kind of lucky that it sort of grazed the atmosphere, right? Rather than coming in at a steeper angle.
Yeah, that's another aspect of it too. It could have a couple of things. You know, obviously it could have been a bigger object, but just the direction of travel for this particular one, it didn't impact straight in, so that helped make it less bad. But also, it's not that large. I mean, this is a relatively small object, and you know, the size of a building, right? A planetarium. So not huge. But enough to break a lot of windows and send about 1,600 people to the hospital.
And we have some other objects we can highlight as well. I think this is the Canyon Diablo impactor.
Yes, so that you can start to see is getting a little bigger, a little larger, moving up in size. And also too, now we've got, let's see, which one is this?
This is Tunguska.
Tunguska, right. So this is an airburst explosion that occurred in 1908. Again over Russia, and it knocked down trees over hundreds of square kilometers. And even though the object is really only a little bit larger than the Chelyabinsk meteor, you can see there, it's a few times bigger, but it's not hugely larger. So in this game, though, the diameter of the object really matters a lot because it's the mass in that kinetic energy of motion equation. The mass depends on the size cubed. So size times size times size, and that really pumps up the kinetic energy for these impactors. Going back to Chelyabinsk, just another thing that made this one such a surprise is the direction that it came from on the sky. It actually came from a direction that was very close to where the sun is, and our telescopes just don't look there. We don't have telescopes that can search that close to the sun. So in this case, the object really came out of nowhere, and that was a complete surprise.
What about what they are actually made of? Like there are asteroids that are more like iron rich versus ones that are kind of more rocky and less dense. How much of that is a factor?
Yeah, so the density, the kinetic energy in the equation of motion, it couples into the mass and it scales linearly. So there's a huge range of densities for these objects, everything from things that are kind of fluffy comets where all the ices have kind of been boiled off and what you're left with is this kind of crumbly, muddy stuff, so to speak, that's all frozen together. So those have a density that can be as low as about water. So something that is just like ice in terms of its density, all the way up to things that are basically solid slabs of nickel iron. And that can have a density that's maybe 8 times larger or something like that. And then everything in between. In this case, the Chelyabinsk impactor, we know from the little pieces that we found on the ground, and some not so little pieces, that this object was stony. So this was a type of stony material. And the one that created Meteor Crater, by contrast, that, however, we know from fragments that have been found there, that was actually an iron, predominantly iron object.
And actually kind of similar in size, right?
Yeah, kind of not too much different in size, just a little bit bigger, but, made out of much heavier and more dense material. So it really packed a punch.
Well, then you mentioned Itakawa earlier, and we have that represented here as well.
Right. This is one of my favorite asteroids. This was the target of the Hayabusa mission, and you'll notice it kind of has a funny shape. Look at that sort of funny peanut shape. Some of my colleagues like to say that it's shaped like a sea otter laying on its back. It's kind of cute. but yeah, that characteristic shape, a lot of asteroids have kind of oddball shapes because they're formed by collisions long ago, and sometimes things may have collided, broken apart, and then reassembled. With Itakawa there, you can almost see kind of around the neck of the otter there are kind of two parts of it, and it almost looks like it was at some point, pulled apart and then stuck back together, and there's a little bit of pond of dust in there too.
Right. Well, then we also have the asteroid that we already mentioned, Bennu.
Yeah, so Bennu is a kind of a fun object here because it's shaped like a top, and you'll notice that sort of weirdo top shape. That, as it turns out, is another shape that Mother Nature likes to make for asteroids. And this has to do with the idea that it's actually a pile of gravel kind of floating in space, you could almost think. It was a huge surprise when scientists got there. In fact, I've got some images of it, and I think we're going to take a look at some other images of the surface of this asteroid. But basically, it looks like a ball of gravel. And one of the neat things is that, it's hard for nature to make these kinds of shapes on the ground because we have the pull of the Earth's gravity. So that funky top shape, we're going to see that again when we look at the next asteroid, I think.
Right.
Which you've got
up here.
Yeah, and this is asteroid Ryugu. So this is the target of the Hayabusa 2 mission that's about to bring the sample back to Earth. And there it is again, this funky top shape.
Oh, yeah.
So for some reason, or maybe it's a muffin. I don't know. What do you think? Muffin or top shape?
And then we have Toutatis here.
Yeah, this is another very large near-Earth asteroid, Toutatis. And you can see that it's kind of that funny club shape, again, sort of the same idea as Itakawa, where you've got the possible idea of maybe two pieces that were fragmented and maybe recoagulated somehow, or maybe it's just a shard of a collision long ago. So these things have typically, they sit frozen in space for many, many billions of years, but sometimes they have some exciting things happen as they get ground up in their journey through space. And here we go, another one. This one is this is actually a comet. This is comet Churyumov-Gerasimenko, or 67P, as it's sometimes called. And it, to me, I don't know about you, but I think rubber ducky when I see that.
Right.
Kind of looks like a rubber ducky. So this was another spacecraft target, and this was the European Space Agency's Rosetta mission that actually went to this object, and even had a little lander that hopped around on it. But now we're starting to get into really big stuff. Yeah. You want to tell us about this one?
This is the Chelyabinsk impactor, estimated size.
I think this one is somewhere between 5 and up to 10 kilometers in diameter. So this is the object that is thought to have wiped out the dinosaurs about 65 million years ago. And it's a very, very big asteroid, as you can see. It's much larger than the comet, and when it impacted the Earth, it was devastating to the entire world.
It's about the same size as San Francisco, give or take. It's a little scary.
Yeah, that's a pretty scary one. So that object, when it impacted it, actually, it really did cause serious damage to Earth's biosphere, and it caused major extinction events. In fact, most life forms that were large just simply went extinct, not just initially because of the blast, but because of the impact on the food chain. Basically, there was a period of global debris lofting and a lot of flaming debris falling down on the Earth. But then there's basically pretty solid evidence that there was a widespread wipeout of the food chain. And that's really what did it for the larger animals. Just there was not enough for them to eat. So basically, these large impacts are capable of causing very, very sudden climate change. So in a sense, our poor Earth has already seen this experiment happen, and it's not a good one to repeat.
Right. And I apologize. I got a little bit ahead of you because I put up an object that will definitely not be impacting us, although pieces of it, I guess, do. That's the giant asteroid Vesta.
Yeah, so now you can see, stepping up in scale, you can actually start to see the curvature of the Earth here to get a sense for just how big Asteroid Vesta is. And you're right, it's a really good thing that this asteroid gets nowhere close to the Earth. Right. This could never happen. What you see here, this is
right. Luckily.
Well, yeah, luckily, this is not a thing. Asteroid Vesta is a main belt asteroid, so that means it stays in the main asteroid belt between Mars and Jupiter, and it stays there. It's been there for billions of years. It'll probably be there for billions more. and it's just doing its little thing going around the sun, and it's happy where it is. It was actually the subject of the Dawn mission, and this plus another object here were both the subject of NASA's Dawn mission that actually went to both of these objects and made really beautiful maps. Do you want to tell us about this one?
So this would be Ceres, and that we always love to discuss whether we call it an asteroid or a dwarf planet or both, but get a good look of how large that is. I mean, really relative to the Western United States.
Yeah, that is the largest object in the main asteroid belt. So it's like you say, it's got a dual designation. It's both an asteroid and a dwarf planet, and that's because of its shape. So you'll notice now that most of the objects we've looked at have had kind of oddball shapes. They're either baked goods like a muffin, or they're kind of potato shaped or some kind of weirdo shape. But now you're noticing that the shapes of these objects are starting to get more and more round. They're starting to assume a nice spherical shape. And that's because what's happening is these objects are now large enough that their own gravity is enough to form them into a ball. And so even Vesta is starting to get to be large enough there to have that roughly spherical shape. Vesta, you can see there was kind of some chunks taken out of it. It's kind of lumpy. It's not perfectly spherical, but it's starting to get there. So by the time we get to something the size of Ceres, now you're talking about something round.
And part of Vesta's lumpiness is kind of going back to the collisions kind of story where it suffered some really major impacts kind of early in its history.
That's right. In fact, I think on its south pole there, you can see there's a huge chunk that was taken out at some point by a pretty massive cratering event. Yeah. So anyway, so this just shows you there's a huge diversity of different types of things out there in what we call the small bodies. Even though you can see Ceres there's not so small. But well,
then to round out the going back in time a very long way, we do have a representation of the really enormous object that collided with Earth very early in our history, and is the potential lunar forming impact, sort of just to give a sense of scale.
Yeah, so this really going back in time to just after the formation of our solar system, so just after everything kind of coagulated out of the cloud of gas and dust, it's thought that there was a kind of a Mars-sized protoplanet, and that's why it's shown with all the molten lava on its surface there. I think scientists have, it's an artist concept, right? We can't go back in time literally, right. But the idea is something pretty massive is thought to have collided with the Earth about maybe say 400 or 500 years after the formation of the solar system, and sort of scraped the crust off, and then this object pretty much vaporized. And that is what is thought to have formed the moon. At least that's one of the leading hypotheses for how the Earth has gotten its wonderful moon.
But definitely a collision that is not going to happen again in our solar system, given that there just aren't those giant objects roaming around the solar system waiting to collide with us, but there are a lot of smaller objects.
Yeah. Exactly. So the good news is that we're kind of in the stable part of our solar system's history, and now we mostly just worry about the smaller objects, the near-Earth object population. And I think you've got a nice video of that there, right?
Yeah. So if we wanted to talk about, we already mentioned, I think what we're seeing here is actually the orbit of Bennu. So one of the first objects that we were talking about as being the target of the OSIRISRex mission. I'm sorry, I just mangled my controls here, so it's going to take me a moment to bring it back up. But we can show the location of the asteroid belt as well.
Yeah, that's right. So most of the asteroids in our solar system are safely between Mars and Jupiter, and they've stayed there for billions and billions of years. And these things are really stable. And they mostly don't get anywhere close to us. So they've been there since the formation of the solar system. They'll stay there for many billions more. They're scientifically very interesting because, like I said, they're this sort of a time capsule, if you will, right? They record the conditions of the protoplanetary nebula that eventually formed into our solar system with all the planets. However, there are ways for these main belt objects and their little fragments to make their way out of the main asteroid belt on timescales shorter than billions of years. And when that happens, these objects can become what we call the near-Earth asteroid population. So if you look there, you can see This is a smaller set of objects. These are just the ones we know about, of course. This is not all of them by any means. These are just the ones that have been found so far. And these are objects that meet a specific mathematical definition, meaning the minimum, what we call the perihelion, or the closest approach to the sun in their orbit, is about 30% larger than the distance between the Earth and the sun. So in other words, these are objects that kind of enter into what we call near-Earth space. And yeah, so these ones are the ones we pay attention to from a hazard perspective.
And these vary quite widely in size. So some of these are rather small, and other ones are quite large. How is the search going in terms of finding the ones that are really potentially dangerous?
Yeah, it's you raise a really good point. There's a huge diversity of sizes. We saw that, you know, in our extreme zoom out, right? Everything from tiny little pieces. And in fact, I mean, the Earth's atmosphere is impacted by tons of actually asteroid and comet material that falls down on the Earth's atmosphere and surface every day. However, there are a lot larger objects out there, and the good news is that astronomers have really put a lot of effort into finding the bigger near-Earth asteroids. So there's a couple of reasons for doing that. All it takes is one really big object. If something the size of, you know, the Chelyabinsk Impact, the one that took off the dinosaurs, if that were to happen again, it would be utterly devastating.
Yeah.
So necessarily, the search has started with these big objects. It also kind of works out that those are the easier ones to find because they're a lot brighter, because they're larger, they're easier for us to spot. And we've been sort of working our way down in size over the years. So the good news is, for the really big objects, the ones that really are capable of these truly globally devastating events, things that can cause extinction events on large scales, most of those have been found. And that means like about 95% of things that are of the 1 kilometer class and larger. So that's great. But when it comes to the smaller sized objects, not so good.
It's a lot of work to be done.
Yeah.
Someone actually asked if there is a satellite set to be launched to search for these objects. And I was just going to go ahead and put up our infrared view of the sky as well, which is kind of a nice segue into how we search for these.
Right. Yeah, there's a couple different techniques that people use to search for these objects, and one of them is to use visible light. And in fact, most of the asteroids that we know about today are found using the same wavelengths of light that our eyes are sensitive to, which means what we're seeing is sunlight bouncing off the surface of the object and reflecting back into our telescope. So that reflected light is great. It works fine in most cases, but it has a few things where it's a little harder to see. And that is if the surfaces of the asteroid are a very dark color. We know that some of them are just exceptionally dark, like printer ink dark. Think do you ever spill the cartridge of printer ink? It's messy and it's super black, right? It makes a really dark smudge. That's what the surfaces of some of these objects are like. They're so-called carbonaceous objects, meaning that they're very carbon rich. They came from far out in the solar system, and they're just dim and faint and hard to see in reflected sunlight. Sunlight bounces off, and most of it, a good chunk of it, gets absorbed. So hard to spot. Another technique we've recently been using, and you're seeing some images from the satellite here, is to look for the heat emission of these objects. So using longer wavelengths of light that we call infrared, we can actually search for these asteroids and comets based on their heat signatures. So the sun hits them, the sun doesn't hit them, the sunlight hits them. Warms them up. That would be something.
Yeah, I go about a collision.
Sometimes they hit the sun, but that's another story. But sunlight hits them, warms them up, and then they actually emit thermal radiation that we can spot. And so some of the images you're seeing there are from a satellite that is in orbit right now, making maps of the sky, looking for asteroids and comets using these infrared wavelengths of light. And we like it because, for a couple of reasons, it's very sensitive to even the darkest objects, because now we're sensing their heat, not how much sunlight they reflect. And it also lets us say something about their true sizes for similar reasons.
That's great. Well, since we're talking about spacecraft, maybe it's a good time to, would you like to start with Bennu or Ryugu?
Yeah, and just to follow up on the question here, because I got sidetracked, but yeah, we are trying to look at, so the satellite we have now that made all these maps is a satellite that was originally designed really to just make maps of the sky for lots of different astronomical purposes, not just looking for asteroids. The satellite, as I like to say, we like to say that it's 10 years into a 7-month mission now. So it's been super duper over time, and we don't know how much longer it will last. So we are trying to work on designing and developing a new satellite that would search for these objects using an infrared space telescope. So basically a slightly larger telescope that has a much larger field of view, so a very wide angle lens, if you will. And the idea is to go out and help complement the ground-based surveys so that we can see the objects, more of them further away, and spot them when they're many decades away from any sort of an impact.
Plenty of warning.
Hopefully, yes, that's the goal. So we'll see. You know, as always, these things these space missions are just really challenging to get done, and it's a tough budget season out there. So we'll see how it ends up going. But we do think this is a problem that it can be addressed if we actually just go out and look for the asteroids. But that's hard to do.
Yeah. Well, I think in the interest of time, maybe I'll start by highlighting Bennu's orbit and maybe take us in a little closer to Bennu and get rid of our psychedelic infrared sky here for a moment.
There we go. Yeah. Yeah. So Bennu is the top, one of the 2 top-shaped asteroids that we saw earlier, and it's a near-Earth asteroid. So this is an object that is falling into this category of objects that we pay careful attention to because it does have the potential of getting close to the Earth, or at least its orbit does. This particular object, the color is not an accident. This thing falls into the category of objects that are just super duper dark. If you were to see it in natural light with your own eyes, or you had a piece of it, which hopefully we will soon, it's going to look really black. It's a very, very dark charcoal gray color, dark, like my shirt here. And that's because it's made out of primitive carbonaceous, really carbon-rich material from far out in the solar system, we think. And so somehow this object has, through collisions and kind of just generally drifting, has made its way into the space near the Earth. So the really interesting thing about it is several things. One, it's actually ejecting little pieces off of it. So it's got little moonlets flying off. Pieces are actually kind of coming off of the asteroid. And you might ask, well, why does it have this weird top shape? What's with the shape? Mm-hmm. As it turns out, we think what's going on there is that this object is essentially what we call a rubble pile, meaning it's a disaggregated collection of rocks, essentially, that are held together by their own self-gravity. There may be some bigger pieces of it on the inside, but the surface is really covered with this extremely textured gravel. It's very, very just loose aggregate of material. Lots and lots of little boulders and rocks all stuck together. And we think what happens is when you take something like this and then you have it spin, because everything has angular momentum in space, most of these objects have some kind of rotation. What happens is it's just not strong enough internally to stick together. So what happens is it starts to form this equatorial bulge, or this kind of diamond shape. And little pieces of it seem to sometimes get thrown off into space. Maybe that's the result of some heating from the sun that just sort of is enough to push the objects off. So kind of like popcorn kernels, maybe. They get on and poof, off they go. But yeah, so it's a really fascinating object. And OSIRISRex, I think we have some video of the sample collection, don't we?
Yes.
Yeah, so the OSIRISRex spacecraft has just made its touchdown and collection of the sample. And it is hopefully going to be bringing back some tens of grams or maybe even hundreds of grams of material from the surface of this. So that's ideally about the size of a baseball worth of material. You can see the canister there. It's a little bit like an air filter. The idea is that this canister drops down or is pushed into the surface of the asteroid, and then a gas jet fires of nitrogen that basically poofs a bunch of gas, and that hopefully pushed a bunch of stuff back up into the collection container there, like an air filter on a car, kind of entraining it. And then the arm retracts, puts it into the stowage capsule, and closes it up. So this has all happened in this past week, which is just incredibly exciting.
Absolutely.
Yeah, so hopefully this precious cargo, they'll spend a little more time at the asteroid, doing some additional mapping and looking closely at the little divot that was dug out there at the sampling site. And then they'll start making their way back to the Earth with the sampling container. And the rest of the spacecraft will stay there.
So how do you, because you've been involved with instrument design and such for different missions. Like, how do you design cameras to photograph things that are the color of charcoal? Like,
yeah, it's pretty challenging. I mean, so there's a variety of different tools that astronomers use, and the biggest one is just multiple wavelengths. So like I mentioned, the visible light, you have to pay careful attention to the illumination angles when you do this, right? Because the object is very dark. If you catch it at the wrong side, you won't get a lot of light out of it, and so it'll be very hard to see anything. So it's a combination of making sure the instrument is sensitive enough, but also it's how you operate the mission. And so the folks that are taking pictures with this camera, I'm sure, are paying very careful attention to the illumination of the spacecraft, or illumination of the target rather, when they're planning the, for example, like the sampling activity. You want to make sure that you can see that there's light. But at longer wavelengths, like I said, with thermal emission, you are actually now, instead of sensing the reflected sunlight part of the spectrum, you're actually now sensitive to the heat that's actually being emitted from the object. So it is less sensitive to having direct illumination from the sun, because the asteroid gets warm even on its night side, and you can see that glow of emission even if you're not in the direct sunlight. So that's one thing. And of course, there's all sorts of other wavelengths. There's X-rays, there's looking for charged particles, and all kinds of neat stuff too. So there's a lot of different ways we can look at these objects.
We have a grateful note from the folks in Chile saying that the new Vera Rubin Observatory is also going to be a great asteroid hunter.
Absolutely, yeah. So there's a very large telescope coming online in Chile, and it'll be the Vera Rubin Observatory. So the idea there is to have a very large telescope that's both sensitive and wide angle. That's really helpful for a number of reasons, because we just want to be able to see further away and take lots of pictures over time. So this is another important tool that we hope is going to help a lot for asteroid searches, not just for near-Earth objects, but also more distant objects. And I think one of the other important aspects of having multiple telescopes searching for the objects is that it's kind of like, I guess one way to think about it is it's a little like security cameras on a building or something. You've got different zones, right? You've got one looking over here and one looking over there. So you have a couple different cameras out there looking at different parts of space. That's one thing. But the other thing too is the Rubin Observatory will work at visible and near infrared wavelengths of light with a little bit of ultraviolet also. And so the idea there is that complementary coverage in wavelength space lets us learn more about the objects and their probable composition. So together, I think these will be very powerful assets if we have both visible and infrared telescopes looking for them. Another aspect that the Rubin Observatory, I think, is going to really help out with a lot is that it's those pesky asteroids in the main belt. It turns out when you're looking for the near-Earth object population, a lot of objects are out there in the main asteroid belt between Mars and Jupiter. And we have this needle in a haystack problem, which is that we have to pick out the near-Earth objects from the more distant main belt asteroids. So building a really good and robust catalog of the more distant objects is going to be a very important component of figuring out which ones really are new near-Earth objects. So I'm really looking forward to getting a much better main belt asteroid catalog, because we really want to sift the wheat from the chaff, so to speak. That's one of the big challenges.
Well, that's great. We're almost at time, but I think we wanted to just kind of wrap things up a little bit with the with some of the objects that, I mean, everything we've talked about so far has been an object that kind of originated as part of our own solar system. But in fact, recently we've actually discovered objects that are sort of visitors from outside our solar system.
Yeah, this has been a huge and fun, exciting discovery. I think one of the neatest parts about doing these kinds of surveys is you always find something kind of weird and unusual. And recently we have had a couple of really weird and unusual visitors.
So I'll just note we turned back the clock to 2015, and we're showing a trajectory. It looks like it's just targeting right at the sun, but this is the calculated trajectory of Oumuamua. Yeah,
this is the first known so-called interstellar object. So this is a I guess you would call it a comet fragment that is actually coming from outside of our solar system entirely. And you might ask, well, how do we know that? Well, the answer is we can look at the orbit. And in this case, it turns out this object is moving really fast. And when we plot its orbit, it is not consistent with a trajectory that is actually something that orbits our sun. It's actually something that is just wandering through our neighborhood of space and happened to pass through our solar system and is going on its merry way. So you can see there, it's a really unusual object.
And so it basically just sort of did a slingshot around the sun.
Yeah, it actually came in from way, 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 way out and on its way. There it goes. So it's pretty unusual because of all the objects that we found, they all orbit the sun except for this one. And until very recently, that was the only object that was known that was like that. People have predicted that there are such objects out there. It kind of makes sense, right? I mean, the space between the stars is not completely empty, even though it's really, really, really empty.
Right.
But the thought is that, yeah, other solar systems have probably, gone through that. In fact, we see them. We see exosolar planets, and we see debris disks around other stars. So it sort of logically follows that there must be little fragments of these pieces, comets and asteroids, just like in our solar system, that are out there wandering around in between the stars. Mm-hmm. And sure enough, that's what we see here. I think you've got another one, right?
Yeah, this is actually Borisov that we're counting. So it's just, I think we're at about approaching 2019 here when it's making its closest approach. And this one didn't kind of do that big slingshot quite as, the trajectory didn't change as much as with the Oumuamua, but still, this was, I guess, the second object that we've discovered that's visiting from outside the solar system.
Yeah, so I mean, it's. I have a saying, and I'm a bird watcher, and I have a saying in bird watching, which is that if the first thing you go out and see is a robin, that might mean that robins are common, Right. So now that we've seen the first one, sure enough, a couple years later, here's the second one. So it does suggest that there's a population of these objects out there floating around between the stars, and sure enough, this is the second one that's known. So one of the big questions will be, where compositionally, how are these different? And of course, I mean, this is just complete daydreaming, but it really would be pretty cool to be able to bring back a piece of that, just because. Really? Talk about old.
So it's just a matter of finding one soon enough to be able to do that, I guess.
Yeah, the problem with these things is they just move at incredible speeds, right, because they're coming from way outside the solar system, and they move relative to our sun just incredibly fast. So it logistically would be very, very difficult to imagine sending a spacecraft to catch up with it somehow, but you can always dream.
Yeah, exactly. Well, thank you very much for taking some time with us today. I don't know if we have any other questions from Facebook. Well, so here's a question about astronauts on the International Space Station. Are they safe from meteor collisions?
Yeah, that's a very important question. So I know the space station does actually maneuver to avoid debris. Mostly, though, that's debris that we've created.
Right.
It's mostly our own space junk, which is becoming an ever-increasing problem in low Earth orbit, especially in geosynchronous orbit. But where the space station is, yeah, they do actually sometimes execute maneuvers where they will turn the space station to avoid bits of junk, or sometimes they'll change the orbit a little bit, I think. As far as whether they've ever had to avoid something that's not created by us, I don't know the answer to that. My guess is that they're probably, in fact, there are meteor observing instruments all over the ground, of course. And there's actually an interesting experiment where people have actually looked for tiny little fragments of meteorites on top of buildings. Reading about that. Yeah, so it's possible that the space station has done some meteor collection experiments, but I don't know the history. I do know they worry a lot about people-created debris, though.
Right. Yeah, I just will note that we have the trajectory of the ISS up here encircling Earth, and you can get a sense of how high it is, and certainly not protected by Earth's atmosphere to protect it from any micrometeorites or things that would dissolve and create things like meteor showers in Earth's atmosphere. So definitely something to think about. I think there was a second part to that question, but I kind of missed it. It popped up briefly. Let's see. Just a question about astronaut safety in general and space debris. So we kind of handled that.
Yeah.
Well, again, thank you very much. I think that's it for the questions. So really appreciate your time. Are you involved with any of the science aspect of OSIRISRex, or are you're just down the hall from?
I'm down the hall. I'm a cheerleader at this point for the project. No, I just moved to the University of Arizona about a year ago, so it's been really fun though to interact with my colleagues and see all the cool stuff that they've got planned. They've got a lot of really exciting science that they're going to be doing with the samples to try to understand what they're made out of and exactly where they came from, what their collisional history was, what their thermal history was. So, who knows? Maybe I'll start learning about microscopes. It seems like it's pretty fun.
Just got to wander down the hall. And when is the sample returned to you back? Or when
it's a couple years from now, so it's a little while. It takes a while to get back to the Earth, and is pretty far away, and it takes time for the orbits to line up just right for them to make the return trip. After that, the rest of the spacecraft is still out there, and it's possible that could be used to go fly by another asteroid.
Oh, wow.
So
a little bit like New Horizons going and visiting another object in the outer solar system could pay a visit to another object.
It's possible. So I'm really hopeful that the OSIRISRex spacecraft will live to see another day, or another asteroid rather.
Excellent. Well, again, thank you very much, and thanks to everyone for tuning in, and anyone who's watching this asynchronously a little bit later on. Stay tuned next week. We're going to be talking about Mars and the cosmic conversation with J.R. Skook from the SETI Institute. So thanks very much. Thank you, Amy. Enjoy the rest of your Friday, and happy Halloween.
You too. And thanks for having me. This has been fun.